We will now study convolutions. This is a very important tool in analysis, especially in the study of partial differential equations and also in probability theory. Okay, so we have already seen this in the context of Fubini's theorem, and so we have the following. I recall the following definition. So f and g integrable over Rn. So Rn will always have the Lebesgue measure. So that is the measure which we are going to deal with. The convolution of f and g, denoted f star g, is defined by f star gx equals integral over Rn f of x minus y gy dmn y for x in Rn. We have seen that this is well defined. In fact, we started with Borel measurable functions and used Fubini's theorem to show it's well defined, and then every measurable function can be written almost everywhere equal to a Borel measurable function, and where integration goes it makes no difference, and therefore we showed that this is also true for Lebesgue measurable functions. Further, we also saw, we have seen that f star g also belongs to L1 of Rn, and norm f star g in L1 is less than or equal to norm f L1 norm g L1. This is a particular case of what is called Young's inequality, which we will now extend. So we will now try to extend the definition of the convolution product to other functions, not just L1 functions. So theorem: 1 less than p less than infinity, f in L1 of Rn and g in Lp of Rn. We have also seen that the convolution product is both commutative and associative. We did it either in the lectures or in the exercises, and we have seen those things. Okay, so f star g is in Lp of Rn, then f star g is well defined, and norm f star g in Lp is less than or equal to norm f1 norm gp. So f star g belongs to Lp of Rn, and norm f star g in Lp is less than or equal to norm f1 norm gp. So if p equals 1, this is the old result which we already have. So proof: we are going to use the duality method. So let p dash be the conjugate exponent for p. So let h belong to L1 Lp dash of Rn. Now you consider the map xy going to f of x minus y gy hx. Okay, and we are going to use Fubini's theorem, Lebesgue translation invariance of the Lebesgue measure, and Hölder's inequality. All of these results we are going to use. So integral over Rn. So we want to know if the integral f of x minus y gy dmny exists. For that we are going to use Fubini's theorem, as we can see now. So okay, so mod f of x minus y gy hx dmny x dmny. Doesn't matter what order, we are taking non-negative functions. So this can be written as, since we are dealing with non-negative functions, so this is equal to mod hx of integral Rn mod f of x minus y gy dmny dmnx. Now we will make a change of variable in the inner integral. This is equal to integral Rn mod hx integral Rn x minus y equal to w. So you have f of w, and then y equals x minus w. So g of x minus w dmnw dmnx. We have seen that how these things are well defined. We have done long ago that we can in fact make such transformations. Okay. So now w, there's only one function involving w and nothing else involves w. I mean purely w, and it doesn't involve anything else. So again, by Fubini's theorem, I can interchange the order of integration. So integral dmnw integral Rn mod hx mod g of x minus w dmn x dmn w. Now we are going to use Helder's inequality because this belongs to LP dash and this belongs to LP. And by translation invariance, w is a fixed vector for each integral, and therefore by translation invariance this is an LP, and then by Helder's inequality, so Helder, you get this is less than or equal to integral over Rn mod fw into norm h p dash norm gp dmnw, and that is precisely equal to norm f1 norm g p norm h p dash, which is less than plus infinity. So by Fubini, for almost every x, you have that the integral of Rn hx f of x minus y gy dmny is well defined. Now choose h in LP dash of Rn such that hx is not equal to 0 for all x. So example of such a function, e power minus mod x square equals hx. We have seen how to evaluate this integral, and this in fact belongs to all LP spaces. So this is a function which you have. So if you substitute that here, so this is Rn here. So that will imply, then you can cancel out the h, so that implies that for almost every x, integral f of x minus y gy dmny over Rn is well defined. It means the convolution product is also by earlier computation, f star g, so this is equal to f star g of x is h going to integral h f star g dmn. What is this? This is equal to integral over Rn h of x integral Rn f of x minus y gy, dmny, dmnx defines a continuous linear transformation on Lp dash Rn. And with norm less than or equal to norm f1 norm gp. That comes from star Cf star. So this implies that f star g belongs to Lp of Rn and norm f star g in Lp is less than or equal to norm f1 norm gp. So this is a nice technique. So you want to show something is in Lp. One way is to show that it is the p integrable. The other way is to multiply it by the Lp dash function and then show that that can define a continuous linear function on Lp dash, and then you can do it. And here we did that, and we used Fubini's theorem to do this. Okay, so in general, so remark, in general, if 1 by p plus 1 by q equals 1 plus 1 by r, 1 less than or equal to pqr less than infinity, then f in Lp, g in Lq implies f star g well defined and f star g belongs to L of R, and norm f star g in Lr is less than or equal to norm fp norm gq, and this is called Young's inequality. So what we have proved so far is a particular case of Young's inequality. So now, so these are the convolutions with Lp functions. Now let fg be continuous functions Rn to R. If at least one of them has compact support, then integral f of x minus y gy dy dmny over Rn is well defined, because you have to integrate. For instance, if g has compact support, then you just integrate over the support of g, which is a compact set. Then f and g are continuous, therefore they are bounded. Compact sets are finite measure, so this integral is finite and therefore it is well defined. Now, so we can define f star g like this. So then theorem, fg continuous real valued functions on Rn, and one of them at least has compact support. Then we have seen that f star g is well defined. Support of f star g is contained in support of f plus support of g. What is support of a function? It is a set where the function is non-zero and then you have to take the closure. Okay, so the support, so outside the support the function is identically 0. So the support of f plus support, where given sets A and B in Rn, A plus B is defined as set of all x plus y, x in A, y in. So this is the algebraic sum of sets. Now proof. So A equals support of F, B equals support of G. One of them is compact, so without loss of generality we take B compact. Because when you define f of x minus y, because by commutativity of the integral, it's f of x minus y gy or g of x minus y fy, it doesn't matter. So you can take any one of them to be of compact support. Then A plus B is closed. Normally when you have two closed sets, the sum is not closed. Whereas if you have one closed and one compact, then the sum is closed. So let xn plus yn belong to A plus B and xn plus yn converge to Z in Rn. Now B is compact, so there exists yn k subsequence. Yn k converges to Y, and compact sets are closed, therefore Y will also be in B. Then this will mean that x and k will converge to Z minus Y, and this because has to be in A. So that means Z equals x plus y, where x is in A and y is in B. That is A plus B is closed. So if A plus B is A, B are both compact, then you can easily see that A plus B is also compact because you have sequences have convergent subsequences, and therefore if Fg okay, so this is just a remark. So A plus B is closed. So now if you look at this integral f of x minus y, g of y dmn(y), it is enough to consider this integral over B. So f star g of x, it is enough to consider this integral over B because g has support only in B, and therefore if f star gx is not 0, this implies that x minus y must belong to A, which is the support of f, for y in a subset of positive measure of B. Only then, so only if this is non-zero for some set of positive measure subset of B will this be non-zero, will the integral be non-zero. In particular, you have x belongs to A plus B. Now A plus B is closed and contains the set of all x such that f star gx is not 0, and therefore this implies that support of f star g, which is the closure, is also contained in A plus B. So in particular, remark, if f, g both have compact support, then f star g also has compact support. So now if you have f, g, h, two of them compact support, then f star g, and you take h, and f and g star h. Okay. Now, if f and g have compact support, then f star g has compact support. If g and h have compact support, then g star h have compact support. So, in either case, whether you take f star g h or f and g star h, both of them, at least one of them has compact support, and consequently you have that f star g star h is well defined, and similarly f star g star h is well defined. And because of associativity, these two are in fact equal, and you can write this as f star g star h without worrying about putting, that means you are defining it 2 by 2. In general, f1, f2, fn continuous, at least n minus 1 of them have, so let us not write like that, all but at most one of them have compact support. Then we can define f1 star fn 2 by 2. The same way as I did for 3 functions, you can define it 2 by 2 for various functions. Okay, so we will continue with the properties of convolutions. So we will show that its utility is, namely, it has a smoothing effect. You can convolve. Suppose I take an integrable function and a continuous function with compact support, then the convolution is continuous like that. So we will see such properties next time.